Well, thank you very much to Yuk, in particular, for the invitation to come and speak to you today on the topics of cybernetics and indeed the future of cybernetics. It's a topic that he and I have had discussions about both, I think, directly and indirectly for quite some time now. And so it's a pleasure to be able to share some of my recent thinking on the topic in the context of this lecture series. As you see the title of the talk, Cybernetics and Artificialization, I'll speak a bit about what I mean by artificialization, which is perhaps somewhat idiosyncratic use of the word. I will also speak a bit where you see something called teleogenesis of nested circuits. I promise to unpack those terms, and by the end, you'll have full understanding of what I mean by that. Let me then begin then. What is the future of cybernetics? This was the question that was posed to me by you with the invitation to do the lecture, which I think is a quite provocative and interesting starting point and framework for exploration, but itself is a question that invites further questioning, which is usually a good sign of this. And we may ask of the question itself, in terms of what is the future of cybernetics, also indeed, what do we mean by cybernetics? Are there ways in which that term itself may be something that changes in the future? Or should we think of the term as something that is referring to a kind of phenomenon or set of phenomena or a set of processes that are consistent or relatively consistent and durable across historical time? And yet their futurity has more to do with the kinds of transformations that they bring about into the world rather than themselves being transformed. So two possibilities, both of which are quite lucid in their spaces of possibility. And then second, indeed, what do we, accordingly, in relationship to that, what do we mean by the future? And I'll try to make the case that much of what cybernetics has attempted to describe is something that is deep in time, is deep in part of the processes by which life has evolved at all. And so given the depth of time, historical time in the past, versus asking about cybernetics' deep past, that is, the question of the future may be one that is non-anthropometric, not askable in relationship to human experience of time, but rather something that exceeds that. On the other hand, much of what I'm going to be talking about today actually has everything to do with human agency, human design. And so let me then begin then with a few different questions about what we might mean by futurity in this sense. That is the question, at least in the West, the very idea of the future as a single conscious, a single thing about which we could speak is something that has its own history, ironically enough. For much of the time of the development of Western civilization, such as it is, the future was understood as something quite deterministic. It was understood through eschatology, that there were mythical, theological, cosmological in the anthropology sense, explanations for how the world began and indeed how the world would end. The book of Revelations of the New Testament being a case in point. In this case, the future was, again, determined. It was up to the present moment to figure out where it was on this course of history, but the course itself was a foregone conclusion. One of the process by which the future was modernized was indeed through a process of secularization. And the real effect of the process of secularization was one that made the future non-deterministic, that was not predetermined, that was open and to a certain extent contingent. And so the secularization of the future was about the introduction of contingency, that the future was whatever it was made to be, that it could be this and it could be something else. On the other hand, and in more recent times, as our understanding of evolutionary processes has become more granular, indeed more theoretical, with greater theoretical robustness, that contingency itself is understood as within a larger context of certain trajectories of path dependency, that once certain things evolve, that it is much more likely that the next things to occur will be this as opposed to that. That every time something appears, it is not only opening up a space of possibilities, it is closing down a space of possibilities. And so that closing down of a space of possibilities is what we call the path dependency. And it structures that the futurity in different ways. Clearly today, when we talk about the future, what we are concerned with climate collapse, general systems collapse, and so the very continuance of historical social time is something that is put in question, indeed, by those concerns. Obviously, much more to discuss here, but in the interest of time, I'll go quickly. When we talk about cybernetics, here's what I'd like for us to consider. I'd like to give a very simplistic and reductive practical definition of cybernetics as a dynamic that is composed of sensing, modeling, and control, a kind of loop. And that if we were to abstract cybernetic processes again to their most reductive and simplistic form, we would find variations on this three-part sequence of sensing, modeling, and controlling. I'm fully aware how much is being amputated by my definition, but I think you'll see that the where I'm going with this will be somewhat useful nevertheless. I want to make the case then, when we talk about cybernetics, that what we're talking about is something that is both discovered and invented. Discovered and invented. That is, the real natural phenomena in the world that can be described through cybernetic language. Gregory Bateson talked about, a man, an axe, and a tree is a cybernetic loop. That the dynamics of cells and how cells autopoietically reproduce themselves is a cybernetic process. That the homeostasis by which a watershed and a forest come into certain degrees of nitrogen balance is a kind of cybernetic system. None of these were invented by people. What people invented was a language, a kind of formalization by which those processes could be described. And so in this sense, cybernetics is a language that describes natural phenomenon rather than a language that describes artificial constructs. And yet, that language, quite clearly, that formalization was used and continues to be used to produce artificial loops, artificial structures of sensing, modeling, and control and recursion. And so there is inevitably a kind of back and forth between the cybernetics was discovered, about which we may have a variously accurate or inaccurate language, and the cybernetics that is invented. For example, the computational systems through which I'm speaking to you now, and to which you're listening to my voice, are all ones that emerged, that were invented through the complexification of cybernetic thought, which connects us then quite clearly with the dynamic of computation. I would make the argument that computation likewise was not only invented, but also discovered. That computation in its most basic sense is a general property of physics. It's a process by which the universe organizes itself. That algorithmic processes are intrinsic in the unfolding and regularization of complex systems. And others would point to the fact that at the smallest and most granular levels of reality, that discrete bits of information constitute our understanding of the fabric of space-time itself, a topic far beyond my pay grade. The main point I want to make here then is that computation, like cybernetics, is a framework that describes a certain kind of natural phenomenon. And then that the computational appliances that we have invented as of now, like the laptop on my desk, are just that. They are they're machines that are capable of low-dimensional approximations of natural computational phenomena. So in this sense, like cybernetics, there we can speak of a computation that was discovered and a computation that was invented. And indeed, it's this dynamic between the discovery and invention of cybernetics and computation that I think will, in many respects, define its, almost by definition, will define its future. In other words, there are ways in which the invention of new cybernetic systems comes to allow for the scientific and descriptive understanding of natural cybernetic systems in ways that would otherwise be impossible. And our understanding of natural cybernetic systems in turn frames and makes possible the agenda for the artificialization of our cybernetic systems in ways that would otherwise be impossible. These two dynamics inform themselves in other words. So what I want to then quickly and briefly speak to you about today in relationship to this are these, in essence, six possibilities here. We have an evolution. That is, we'll call that the process by which natural cybernetics appears, evolved forms of sensing, evolved forms of modeling, and evolved forms of control. We also have artificial sensing, modeling, and controlling. And we should think of all six, when we're talking about cybernetics in the past, present, or future, and especially the future, we should think about all six of these as the constituents, as the variables that are part of the mix. So what do I mean by evolution in this sense? Well, again, this obviously deserves its own discussion in its own right. I will make the simple point here, or perhaps not so simple point here, that when we're speaking about the evolution of complex living systems, that we are absolutely, for sure, speaking about the agency of chance. And the chance mutation and the processes of selection that arrive and ultimately compute, if you want to extend the metaphor, integrations and systemic relationships between evolved things through selective processes that not only respond to the agency of those things, but indeed produce those things in the first place. That anything that evolves, its shape, its form, its anatomy, its chemistry, is the result of selection pressures. At the same time, it's impossible when we observe what was called in theoretical biology is called convergent evolution. That is, given a set of circumstances, that a certain kind of outcome is much more likely to happen. For example, that vision evolved many times throughout evolutionary history with completely independent lineages and trajectories, that crabs, of all things, evolved many times. And we see technical convergence evolution of the number of cultures that independently arrive at techniques like writing or wheels and so forth. What this suggests is that chance isn't the only variable here, that in essence, chance is on rails. That chance is that there is, to a certain degree, a kind of opening up and closing down, again, of path dependencies and spaces of possibility, and that there is a structure and pattern to that as well. I understand that this is not entirely a confirmed point. So that then to our six variables. Sensing, in this sense, we're talking about evolved sensing. So some examples of evolved sensing with which we're familiar would include the evolution of vision, the capacity of chemoreceptor cells to evolve into photoreceptor cells, and then those in turn to ultimately drive the evolution of brains capable of processing the light into more complex information that is used later in modeling. Touch, even very simple organisms are able to respond to inputs from their external environment, be those physical proximity or chemical transformations, that the ability of an organism to measure and respond to changes in its external environment is also sort of essential to its, not only its survival, but its coherency as an organism in the first place. Audition arrives much later. The capacity to hear, to detect transformations in air, which we interpret as sound, the waves transformation of this as well, also evolves in some organisms much later on, but provides a different kind of orientation. Similarly for smelling and indeed tasting. Now, the point I also try to make here is that in the being too again, too reductive here, but that in many cases, these natural capacities for sensing precede the evolution of anything like a complex brain-like organ that is capable of processing these information. But indeed, that the brain evolves in the response to the, let's say, to the pressure necessary to model increasingly complex forms of sensing. That it perhaps in a predator-prey dynamic, that the capacity to process sensory information with greater fidelity or speed becomes an evolutionary advantage, but that the sensing precedes the modeling, both in my schema, but also more importantly in actually an evolutionary time. So then what do we mean by modeling then? Well, some examples of evolved modeling would not only, would think of like the things that a brain might do. Well, let's be more specific than that, and also to a certain extent more universal. What we observe is that even very simple organisms have the capacity to a certain extent to measure and to respond to differences between their present state and their future state. There's whether or not there's in terms of how it is that they're sensing their external environment. For example, if they are able to sense that there is something that corresponds to food, they sense in a particular direction, there's an anticipation at work that if they move in this direction, that food will be available not at the immediate present moment, but at some point in the future, and that if the organism is not particularly hungry, it won't move in that direction. It won't make the calculation, the trade-off, and indeed to sort of go in this direction. So there's some future state, present state. And again, when we think about ourselves and the way we move through the world, crossing a street, buying something in a supermarket, and so forth and so on, we're much more complex negotiation between present state and future state. But this is a part, quite obviously, part of the sort of fundamental grammar of evolved modeling. One of the other more important forms of social intelligence is not only modeling our own mind, but modeling the mind of others. Predator-prey dynamics, so the ability of a predator to model the mind of its prey, the prey to evade the predator by modeling its mind to escape or hide or something, is also an important part of this as well. And so all of the sensory information comes in and allows for the capacity of modeling both the present state and a future state, one that's desirable or undesirable. We model ourselves through things like a body image, or the proprioceptive body image, a perceived body image, but we all have a sense of the coherency and limits of our body, one that is obviously augmented by technology. Most of our body we can't directly sense. I can't feel my liver or my kidneys at the present moment, fortunately. But they're part of the body image. They're part of the boundary of this as well. And so this is also a kind of modeling. Now, the most important forms of complex social intelligence involve not the modeling of present and future state for myself, but the communication of this to others. The emergence of the complexification of social intelligence into collective intelligence comes through the capacity for some creatures, such as humans, to entertain counterfactuals. That not only is it thinking about a present state, but thinking about multiple possible present states and using these little simulations of the future as a way to negotiate and strategize our responses to an environment. These success becomes the impetus for the need for an abstraction of those counterfactuals into symbols that would allow us to communicate those possibilities to one or another. And the rise of symbolic culture in Paleolithic and later Neolithic times, what we might think of as symbolic counterfactuals in the form of writing and images and so forth. These are all forms of modeling. There's obviously many, many, many more, but just to give you a little sense of what I'm talking about. So we also then have an evolution of control systems, things like membranes, the skin and boundary of a cell, the interfaces that allow the certain forms of a membrane, that the purpose of which is to allow to incorporate parts of the outside environment or to expel parts of the inside environment into the external environment one way or another. The point by which information or matter or energy is moved from the inside to the outside are the interfaces. Body plans themselves, the construction and disposition and literal organization of the body as systems become more increasingly complex, is a kind of control system. At a larger scale of population, selection is the key control system, that certain populations will expand or contract over time in relationship to selection pressures. That mutations and the chance dynamics of evolution are either successful or unsuccessful through the control mechanism of selection. Later, we talk about, as cultures become more complex in terms of symbolic counterfactuals and symbolic communication, language becomes a delimiting factor in what is possible to, and how it's possible to communicate different kinds of sensing and modeling information itself. And indeed, all of this is not taking place in a vacuum, but on a planet. The climate in which we have evolved and from which we have evolved is itself something that has a membrane in the form of an atmosphere, but also has its own kind of regulatory dynamics upon which we are fundamentally dependent. So this is what I mean by evolved sensing, modeling, and control systems. Now, let's complexify this a little bit and talk about the ways in which systems might interact with one another. So here is your generic system. You can imagine it like a little cell, or perhaps it's a person, or perhaps it's a country, or perhaps it's a company, or perhaps it's any agent you imagine you might want it to be. But here is a sort of a single one. Now, not only is it in the world, it's not blind, deaf, and dumb. It has some sort of sensory capacity. It's able to sense the world around it and to make decisions in relationship to that as well. It's also not the only one. It may live in a population of similar agents, all of whom also have a sensory capacity to sense their own world around them. And in this case, you see part of what they're sensing is each other. And so what you have then is, as agent 1 is sensing agent 2, and agent 2 is sensing agent 3, and agent 3 is sensing agent 4, and agent 4 is sensing agent 1, so forth and so on, that not only is one sensing the other and the other sensing the other, but they're beginning to make decisions about how they might move, what their present state or future state is, not only in relationship to themselves, but indeed in relationship to one another. And that this back and forth dynamic becomes one of the control mechanisms by which those interactions become more systemic. Now, these may live in a population, but as those interactions between the agents become more complex and more regularized and more stable, those agents themselves come to constitute not, each one of these may be comprised of lots of little subcomponents, but they themselves become subcomponents in a larger system as their interactions begin to cohere and become relatively stabilized. They become, in essence, punctualized, if you like, or aggregated into a singular system themselves, which in fact may have a membrane and a boundary around it. But you see where I'm going with this. That system itself has sensory capacities that it is used and able to make sense of its external and internal environment. Remember, all of these are modeling themselves as well as modeling the external environments of the whole time. And of course, not only are these aggregate agents comprised of subagents, but they are themselves not the only aggregate agent that exists in the world. And indeed, they begin to intercommunicate and start to model themselves in relation to those communications. And hence, we have a kind of fundamental cybernetic system. Now, what I have here is a disclaimer over the top that the way I've told the story is a sort of simple, one into many kind of narrative, but that's not necessarily the way evolution actually worked. It may very well have been, in many cases, the other way around, where it is the aggregate system that produces the internal organ, produces the internal subsystem as a result of the external communication. You see, it may not be that you've got a subsystem that then produces an aggregate system that then enters into relationships with another system. It may be that the dynamics of the two larger systems are the things that produce the smaller systems themselves. Both of these are equally important. Now, what do I mean by artificialization in this context? We were talking about the next 6 of this. Well, I'll write about this in the chapter for you, but I'll try to summarize a little bit of the ideas here as well. One of the key ideas in cybernetics is, of course, autopoiesis, names the ways in which a system is capable of producing and maintaining itself in unitary space, usually by incorporating and transferring energy, information, and matter from its external environment. However, artificialization refers to what we call allopoiesis. That is how a system is capable of producing something extrinsic to the system itself, it produces something outside of itself, usually by transforming energy, information, and/or matter in its external environment, oftentimes through goal-directed action. So you see the difference here. Allopoiesis is the self-reproduction of the system itself by the system. Allopoiesis is how the system produces something external to itself. Artificialization is all about allopoiesis. I'll also make the point, when I have a bit more time, to talk about the ways in which our kind of neo-cybernetic moment is one in which functional definitions of life and functional definitions of technology are at a kind of paradigmatic level, becoming more and more convergent. At different points in time, those terms become very divergent. We describe them in very different terms. But what we're seeing now is a kind of convergence of these terms, which is something that I think will require greater explanation. But today, I will introduce it only parenthetically. Now, when I talk about artificialization, let me explain a few things I'm not talking about. I don't mean artificial as in fake, as in that this is like not real, or that this is an imposter. Nor do I then mean it as something that is opposed to natural. As you'll see, it's actually quite the opposite of this. I don't mean it, that is, I don't mean it as something that is opposed to evolution, but rather as a capacity that evolution has selected for. That is, certain species, certain kinds of organisms, if you like, Homo sapiens being chief among these in certain respects, have the capacity for a tremendous degree of allopoietic intelligence and facility and capacity. We can remake the world through a greater degree than any other species that we know of, for better or worse. And this capacity to allopoietically reconstruct the world around us has what we can call it anthropogenic climate change, is one name for it. But it is something that is inseparable to our growth as a species, and our capacity to capture and make use of enormous amounts of energy, of information, and matter. So then I'll explain this in a bit more detail, but let me then quickly go through a few different possible definitions of artificialization for our uses here as well. One has to do with what we call is that evolved capacity that I've already spoken to here as well. That if evolution has selected for the capacities of some forms of life to capture a greater degree of energy, matter, and information through allopoietic complexification, through the technologization of the world. This has made their expansion and their capacity to replicate something that is intrinsic to that capacity itself. Now, if we zoom out a little bit from there, and we get a little bit more theoretical and draw a bit on information theory, another way of thinking about artificialization has to do with what we might call anomalous regularity. That is, we can detect, if against background entropy, we can detect something that is artificial to the extent to which it expresses a kind of anomalous regularity. The example I'll show you is this image of a forest in Japan. Any of us could look at this image and tell right away which trees were planted by people and which trees just happened to grow there through random evolutionary processes. Why? Because we observe some kind of anomalous regularity in the system. And it indeed is that as anomalous regularity is a sign of what we might, a sign of artificiality, which is itself then an indicator of intentionality, that somebody or something meant it to be this way. So we can deduce intentionality from that artificiality. The astronomer Avi Loeb at Harvard, who perhaps quite fancifully imagines that the Oumuamua object, interstellar object that passed through our solar system some years ago, is an artificial object. And part of the ways in which Loeb tries to make the case is to demonstrate forms of anomalous regularity in the object that suggests that it must have been intentional in some way as well. What is called the glitch in the matrix effect, when we perceive something in the world that just seems too anomalously regular. The implication of this is that somehow reality itself is artificial, that it has been constructed or designed and composed deliberately, and indeed the glitch or the mistake that reveals this artificiality is our anomalous regularity. So I think you see the point. Now, a more anthropological definition of artificialization may come from Terence Deacon, who speaks of what he calls teleogenesis. Teleogenesis is then our name for that intentionality, that we might imagine counterfactually something in the world, and then deliberately, as a goal, construct an artifact that matches that mental model of the world. That there is there's a teleology in the genesis of the thing, hence teleogenesis of the object. And obviously humans are particularly good at this. One of the areas that I've explored just a bit more has to do with Sarah Walker and Lee Cronin, the authors of assembly theory, who offer what we may arrive at as a more mathematical definition of the artificialization, which I'll save for the paper. It's rather mathematically complex. Lastly, then, on this as well, and I know this will sort of end this little detour into artificialization theory, is the ways in which artificialization, the detection of artificialization, allows for not only a perception of agency from outside, like in the forest, but indeed an agency from the inside. Climate change being the kind of key example here as well, what we call agential self-recognition. That is, humans were doing climate change, or Capital, or Cthulhu, or take your pick, was doing climate change for long before we knew this was happening. And now that we do know that it's happening, that the artificial nature of planetary systems is, in this sense, non-negotiable. It is inevitable in the most frightening sense. But what we see here then is that the agency preceded the subjectivity. How did that subjectivity come to recognize itself? It came to recognize itself through climate science, through computational climate science. It was able to recognize the artificiality recognize its own agency in measuring the artificialization of the external environment through measuring transformations in chemistry and so forth and so on. And so when I begin with very simple organisms may understand their environment, present, future state in relationship to their ability to sense transformations in chemical environments, so too for very complex systems such as human societies that are able to measure transformations in their environment through the sensing of chemistry in a much more complex way. So without getting too wordy about it, we might say that we might then define artificialization as an evolved capacity for intelligent teleogenic action to allopoietically produce objects of unevolvable complexity, in which the agent recognizes anomalous regularities and so perceives these as manufactured artifacts, and in turn comes to recognize and subjectivize its own agency in their effects, even if they were not intentional at all of which may reflexively contribute to the natural and or artificial selection and evolution of that agent themselves. Okay, now back to our regularly scheduled program, which will have to do with artificial sensing, modeling, and or control. The important thing where I began with this distinction, this coupling of natural and artificial cybernetics, and then also natural and artificial computation, was for a reason. And that is, in present day, and when we're thinking about the future of cybernetics, the future of cybernetics will also involve lots of forms of artificial sensing and modeling and controlling. The primary technology of artificialization of the present and the foreseeable future is itself computation. It is this essential technology indeed as well for the artificialization of intelligence itself. That is, intelligence was the thing that made previous forms of artificialization possible, and now artificialization is being artificial, or now intelligence itself is being artificialized, which will have obviously considerable consequences. The artificialization of sensing, then, we see examples then of artificial sensing in lots of forms. The machine vision in multiple forms, robotics and artificial touch, biochemical sensors of various kinds, many of which have contributed to climate science, presence in heat sensors, structured and unstructured data. Indeed, the way in which our AI systems sense the world is through structured and unstructured mathematical data, but indeed they are sensing it. Artificialized models would include the aforementioned large language models that produce abstractions of abstraction itself as mathematical matrices. We have various kinds of scientific simulations, descriptive and predictive simulations. We have experiential simulations, that is, through things like VR and XR, the production of complex counterfactual realities that we might entertain together. All of these, in some sense, may result in or be the result of forms of formal probabilistic reason that allow us, such as through climate science, to anticipate much more complex forms of future states than we would ever be able to do so through dead reckoning or just natural perception, which allows for a different kind of intelligence, that is, anticipatory and structural recursion rather than just sense-response dynamics. And then lastly, we would then talk about artificialized control. Artificialized control works through many different sorts of ways. We might see it through standardization, through, for example, the metric system that standardizes the length, width, and height of objects, not only in a descriptive form, but indeed a prescriptive form, which allows for the organization and delimitation of potential future systems to the extent to which they cohere with or against those forms of standardization. Which allows for different forms, indeed, of anticipatory limits, back to climate science for a moment. There are many ways in which the human societies are organized through artificial membranes and boundaries, which we call borders between nation states. But there are many other kinds of boundaries and forms of internalization and encapsulation, as Sloterdijk identified in the third volume of the Spheres trilogy, for just as a sort of reference of an example. But indeed, as we begin to think about the future and things like climate politics, the enforceability of predictive simulations, and not only is that we have a simulation of what the year 2050 is going to be like, but indeed, we wish to prevent that future from ever happening. This is an enforceable predictive simulation and its result may be, for better or worse, take the form of direct subtraction and indeed suppression of some alternatives. And so for artificial forms, the same recursive production of elements happens as well as for hybrid forms. That is, some systems are both natural and artificial at the same time. For both artificial systems, the same kind of nested recursion, of nested circuits that I spoke of in relationship to natural cybernetic systems occurs here as well. And so then lastly, the last slide has to do with a little bit of the moral to the story, and for us to take a step back and to think about all of this as suggested in relationship to climatic systems. We might see a tendency to a certain degree over the course of history of a tendency towards an evolutionary selection for aggregation. That systems grow into larger systems, become encapsulated into yet larger systems, encapsulated into yet larger systems, encapsulated into yet larger systems. That aggregation itself it has a momentum of its own. And in recent millennia, this has been highly adaptive. We're uncertain at the moment whether or not that will continue to be the case, given the present precariousness of results of anthropogenic environmental artificialization. Which raises then the next question of whether artificialization itself is ultimately evolutionarily adaptive. Clearly, it was in the short term. I mean, by short term, I mean the last few 100,000 years and the emergence of Homo sapiens as a species, particularly adept at artificialization. But in the long term, it may in fact burn itself out. So we're used to asking, in many senses, then is technology adaptive? That part of the whole ethos of environmentalism is to question the adaptive nature of technology itself, understood as some sort of separate from intelligence and life itself. But now we're asked to ask a more fundamental and I think even more uncomfortable question. There's whether intelligence itself is even adaptive, whether the capacity for complex life is itself self-extinguishing in the long term. I don't think that it is, but I think it's something will have to be proven rather than just presumed. Now, thinking about then in the future of cybernetics, if you think of my diagrams of all the little nested systems going forward, what we see is then a tendency towards greater and greater aggregation. I think one of the things that Yuke has asked us to think about is the necessity for disaggregation, the necessity for the segmentation and separation of previously aggregated systems into into systems that are disaggregated, that in fact may be smaller in certain extent, but maybe just as complex in terms of the number of subsystems that they compress, but which are not entirely encapsulated by supervisory systems, but may in fact be a kind of final level of membranization in and of themselves. Now, there's a tendency, obviously, to think of that process of disaggregation as a means and end in and of itself, as a good by itself. That the greater disaggregation that is possible, that this reproduces, this extinguishes forms of hierarchy, forms of subordination in both the literal and metaphorical sense. I don't subscribe to this. I think that in many ways that the complexification of life, complexification of intelligence is a precious is a precious evolutionary accomplishment, and one that obviously depends upon the aggregation of multiple subsystems in and of itself. The question, though, is what constitutes a long-term viability for complex life and intelligence on Earth, and wherever else it may emerge, and what are the optimal dynamics of aggregation and disaggregation of complex cybernetic systems, both natural and artificial, that are necessary to realize this. The last point I'll simply to make is that whatever those are, whatever that composition and balance may be, it's something that will have to be composed into existence. That is, it itself will be artificial. So the future of cybernetics is obviously artificial, or it will have no future at all. Okay, thank you very much.